Let's review the problem that we did this previous day. Like I said before, I would want for all of you to do a t-table in which you can place all of your knowns and unknowns. Actually, let me put my knowns in this case in here and my unknowns in here. As I read through this, I'm given the diameter. So I know that diameter is going to be equal to 10 centimeters. Okay. I also have the temperature. So a 10 centimeter diameter copper ball is to be heated from 100 degrees to an average temperature of 100. There was supposed to be temperature here of 150 degrees. Okay. So my delta T, it's just going to be 150 minus 100, which it's going to be 50 degrees Celsius. Okay. Let me move this one just a bit more to the side so I have more space. And time frame is 30 minutes. So our time, lowercase t, is 30 minutes. What I want to do actually in here is I want to convert this into meters and this into seconds. Okay. And since I have 10 centimeters, the way to do that, I want to go from centimeters to meters. So what I need to do is I need to divide that by 100, because centi, 100, which is going to give me 0.5 meters. Okay. Now, and I'm going to use a radius for volume later on. So I'll just divide this by 2. So if I divide this by 2, I'm going to get 0.05 meters. Okay, again, this is going to be divided by 2, so 0.1 divided by 2 will give me 0.05 meters. So now this becomes my radius. So I'm just going to place it over here. Radius is equal to 0.05 meters. Okay. As you have my diameter, that has not changed, that's still the same. Now for my time, I want to go from 30 minutes into seconds. So 30 minutes. And in order to do so, I would want to cancel the minutes. So I know that in 1 minute, I have 60 seconds. My units of minutes cancel out. I end up with 30 times 60 seconds, which is 1800 seconds. Okay. So this here, my time is 1800 seconds or 30 minutes. Same value, nothing changes. Okay. So I got the diameter, I have the change in temperature, and I have the time as well. Another thing that I'm given is the density. So I have the average density and the specific heat. So density, it's just going to be 8,950 kilojoules. So, oh no, density is kilograms over meter cube. And my density is the one that has a kilojoules because it's specific heat. No, yeah, my specific heat is the one that has a kilojoules, my bad. So then this here is just going to be equal to 0.395. Okay. Three, 9, 5 kilojoules times kilograms times degrees Celsius. Alright? Now, that's what we know. What is it that we want to know? Well, we want to find the energy transfer. So for the energy transfer, our formula is going to be Q equals to mc delta T. Okay. I mean, we can also put the volume formula here, but we'll do it later on. So then also the rate of energy transfer, which is Q dot, is going to go to Q over my delta T. And then the heat flux, which is lowercase q dot, which at the end of the day, it's just going to be Q dot over the area. Okay. Well, in order to get all the way to the heat flux, we need to figure out our Q dot. Okay. We need to figure that out. But in order to figure this out, we need to know what this here is, the energy transfer. And essentially we have everything. We know that we have delta T, okay, the temperature, we know what that is, so we can just put a check mark. We know what the specific heat is. The mass is the one that we don't know, but we can find what that mass is, right? If we remember, we said that the density is equal to the mass over volume. In this case, we want to know what the mass is, so we can multiply both sides by volume. They cancel out. And now I end up with mass is equal to volume times the density. I know what the density is. I can figure out what the volume is in this case. Okay. Now volume for a sphere is equal to 4 over 3 pi radius cubed. Okay. So the way that I'm gonna go ahead and do this, space. The way I'm gonna do this is that I'm going to write down my formula. Okay. I know that Q equals to mc delta T. But again, I don't know what the mass is. I do know that it's equal to that. So I can rewrite it as Q equals to volume times density times the specific heat times delta T. Okay? I can also replace this volume formula. I can replace it with this, which is 4 over 3 pi radius cubed times specific heat times change in temperature. I've not changed anything. I've only rewritten everything. All the values are the same. Okay? Now, I can just start substituting values in here. So that'll be 4 over 3 pi. I know that the radius In this case, it's going to be 0.05 meters. Okay, and there's going to be raised to the third. Specific heat, it's here, okay, which is going to be 0.395 kilojoules times kilograms degrees Celsius. And so then times the density. I did forget to put the density in this case. So my density is here. I need to include it over here as well. So density, I'm not gonna have enough space to write everything out. So let me just rewrite everything down here. So then Q would equal to 4/3 pi times 0.05 meters, and this is all raised to the third, times, now let me include the density right here. Density, it's 8,950 kilograms times meters cubed. Okay, so that's checked. Now I can do the specific heat, which is 0.395 kilojoules times kilograms times degrees Celsius. Okay, so that one's checked. Now I can do my change in temperature, my delta T, which is 50 degrees Celsius. All right, now again, I want to double check my units. I know that my answer, or the units for my answer, has to be in joules or kilojoules, right? So let me start canceling units. Degrees Celsius, they go away. So that's good. Kilograms, they go away. These meters, once I raise it to the third, I'm gonna have m cubed. So this goes away with that right there. Okay. And the only unit left is just going to be kilojoules. Okay. Which is what I want. Now, after you do all of this in the calculator, okay, once you plug in 4/3 times pi times 0.05 raised to the third times 8,950 times 0.395 times 50, if you did everything correct on the calculator, your answer should be 92. Let me put it in black. Should be 92.6 kilojoules, and this is after maybe some rounding off. Okay, so that's the energy transfer right there. Now we can finally start solving for the rest, and the rest is just super easy because now the rate of energy transfer, which is Q dot, is just equal to Q over delta T. But we found out that that was 92.6 kilojoules, and also the time frame, if you guys remember, it was 1800 seconds, right? All you have to do is just put this on the calculator. Once you divide it, you will get 0.0514 kilojoules per second. Which you wanna take it a step further. We know that in watts, this is essentially 51.4 watts. Now how did I get 51.4 watts? Well, because I have the kilo, so K is, has a value of 1000, so I can essentially move the decimal 3 times 1, 2, 3. Or I can just do 0.0514 times 1000. Again, this here is the K, which will give you to 51.4, which is that. Okay. Okay, so now we have that. Now we can find the heat flux. So heat flux is just equal to this here over the area. Well, we just found that to be 51.4 watts. Area, we know that's pi in d square, so we're gonna go with that. So 51.4 watts divided by pi times 0.1 meters raised to the second. Once you plug this into the calculator, you should be able to get 1636. Again, this is after maybe you might have done a little bit of rounding off. So then we have our answers in this case. We have the heat flux, we have the rate of energy transfer, and we also have the energy transfer. Okay, so that's what we have. I hope this helps.